Hello, everybody, and welcome to the 17th episode of the Hyperthesis Podcast. My name's Liam.
My name is Feely.
I'm Patrick.
I'm Scott.
So today we're joined by another guest, our second guest, a friend of mine I went to high school with, Scott Young. He did his Bachelor of Science and Master's in Physics/Chemistry at Dalhousie University. He's doing his PhD at University College London, where he studies lithium-ion batteries in advanced characterization via X-ray computed tomography. So we'll get Scott to explain what that means at some point. But first, we'll talk about some interesting news that happened in the physics community recently. So NASA, they successfully completed their first kind of asteroid defense test, where they shoot a satellite into an asteroid to kind of deviate its path. Patrick, I think you might have more to say on that.
Yeah, so I watched the live stream for this, which was 2 days ago, I believe. And so what they did was they launched this probe, sent it out to an asteroid, and actually it was two asteroids, one orbiting the other. And their intent with it was to see if we could slam a high energy, or in this case, high speed, projectile into an asteroid to alter its orbit. And so this is a lot easier to do with smaller objects, hence why we chose asteroids instead of, say, a moon or something. And what we did was we aimed at the orbiting asteroid, so it was quite a bit smaller than the larger asteroid that it was orbiting, slammed it in at about, I think it was about 14,000. It was either miles per hour or kilometers per hour. It's American, so it's hard to say which is which there. But they were able to slam this probe at very high speeds into this asteroid. And now what they'll do is they're monitoring the asteroid and its orbit around the larger asteroid. Just to reference, the smaller asteroid that they slammed the probe into is called Dimorphos. And so it's orbiting this larger asteroid, and they expect a change in orbit since they slammed this probe into it. And they'll be monitoring that with telescopes. And the, I believe, European Space Agency is also sending out a probe to that same asteroid system to monitor and really finely judge the changes in orbit of this smaller asteroid Dimorphos.
How big is this small asteroid, roughly? Or do we know?
That's an excellent question. It is about 160 meters in diameter.
Ooh.
And it's just pure rock. So it's quite massive, but as people who have taken a physics course know, even a little bump can have a nice change in momentum, depending on speed. And also, in this case, there's no really impulse to measure because it's assumed that the impact caused the probe to just completely shatter and get absorbed by the asteroid. But again, we're still waiting on results. It will take a while, but we'll see what happens.
I think it's just fun to think about these kind of celestial mechanics because it's, in a way, because there's no table or there's no floor, right? So everything is moving in 3 dimensions, kind of freely moving in its own orbit, just following its own course that we try to alter it. So I hope we don't have to do the Armageddon thing where you have to, I don't know if people still remember that movie where people had to send in astronauts, the bravest of all, to drill and nuke the asteroid.
Yeah, there were definitely references to Bruce Willis in the live stream itself, which is the movie you're talking about. So it was pretty funny, just where life, I guess, is imitating art in this case.
Other thing, this is not new in the science community. Actually, it's kind of, yeah. Okay, I was reading up on the Unruh effect. I don't know if I said it correctly. I think Liam would have some more idea about that, because it once what this is a project that got away. So I could have worked on that in my undergrad research, but I didn't. So I'm reading up on it to talk to the theory club, to get them to know about the Unruh effects. And yeah, it's pretty interesting. It was basically the theory says that if you accelerate really fast, so have high acceleration, you start to release thermal energy. So it's kind of strange that the faster, well, it's not even faster you move, the faster you accelerate. So you don't have to move fast, you have to accelerate fast. You start to glow. So it makes me think of, the pop culture movies and references where the people move really fast, go through space really fast, and they start to glow. Like, well, that's kind of has a theoretical foundation on it.
Yeah, so I know a lot about Unruh radiation. First predicted by William Unruh at the university. Well, I don't know if he was there when he predicted this, but he's at the University of British Columbia now, I think. But yeah, so Unruh radiation is actually a form of pair production. It's very much related to the Hawking effect and all this other stuff. But yeah, like exactly what you said, as an observer who's undergoing constant acceleration, as their speed becomes closer and closer and closer to the speed of light, they observe kind of thermal particles peering into existence as if they're in some kind of thermal bath.
Yeah, and fun fact is like I think my current supervisor, when he was at UBC, I think his workplace is like right beside Unruh's office. I was like, interesting. Yeah, because I actually really like how they derive it and stuff. But I think what's make it new, I think this year in the summer, they started to try to do it experimentally to find some evidence on it. They found something. I haven't read up too much on it, but because before it's kind of controversial. Like maybe some people don't believe it's real. Some people say is can happen. How can he? It's self-observed having some thermal energy just from acceleration. It's kind of really strange thing. So I think in a few years, maybe there gonna be some good evidence or good anti-evidence on this effect.
I think, yeah, there's one paper I've been meaning to read, which is called, it's like Unruh detectors, or interferometry of Unruh detectors in Bose-Einstein condensates, or something like that. And yeah, they've actually come up with an experiment to detect it, although they have to make it. But yeah, I think Unruh radiation is definitely a real thing. It's so much related to Hawking radiation. It's not quite the same thing, but it's like pretty much the same thing mathematically. And you, in a space-time diagram, which I won't get into because people don't like math, and fair enough, math is scary. But in a space-time diagram, you're approaching a horizon. In an Unruh, an accelerated observer is actually approaching a causal horizon, very much like an event horizon of a black hole. So anyway, maybe we should talk about that in another episode.
Yeah, but I think the prediction is to have observable effects. The acceleration has to be like 1 trillion meters per second square or something absolutely ludicrous.
Yeah, it's like 10 to the 30 meters per second squared, or 10 to the 28. It's ridiculous, and it's like the this other thing called the Schwinger effect, which is another form of pair production. And the Schwinger effect is that if you fire an electric field that's strong enough, like 10 to the 28 whatever, you can excite particles out of the vacuum, so you can just create stuff from nothing. And they're all very much related, and that's a lot of what my PhD research is on. But enough of that.
Perhaps it's not nothing. Perhaps it's ether.
Well, the quantum vacuum fields, or whatever you want to call them.
Anyway, with this interesting stuff, and again, it sounds like we'll have to do a episode on relativity, just so that people who might not be familiar with them can understand space-time diagrams and Lorentz invariance and all of this fun stuff. But moving on to our main topic, is Scott talking about research.
Okay.
Yes, Scott, my man. Tell everybody about yourself a little bit. So, what got you? Yeah, so what got you into science and whatnot? Because we went to high school together way back in the day. We took all the science courses together and so on. So what got you into science?
Well, science is, I guess, not a challenge, but it is yeah, it's a challenge in a way, I guess. Like it's very interesting, and there's just no barrier to when you can stop learning. For instance, like you could focus on one little thing and become an expert, but there's still a trillion other things that you could dive into. Imagine it like an infinite array of rabbit holes that you could get stuck in, and so definitely keeps the interested occupied. Let's say.
Yeah, as you figure one thing out, you tend to open about 100 new questions. So, yeah, the infinite array of rabbit holes. That's interesting. So you went to Dalhousie in Nova Scotia to study. Well, I believe you took some kind of interdisciplinary science program at Dalhousie, and then you settled on kind of physical chemistry, or maybe that's not the right term. You tell me. So what did you do at Dalhousie while you were there?
Yeah, so it was mostly focused on physics to begin with, but then materials really caught my eye, and I seen that there's big advantage of understanding things from a physical aspect in materials, but also a chemical aspect. And also with regards to quantum, I kind of finished all the physics-based quantum, but then there was a whole like series of chemistry-based quantum. And I thought that having both perspectives when going into specifically material science would be probably the best to understand it fully.
Yeah, I always think it's interesting how physicists approach quantum mechanics very differently than chemists do, or pretty much anyone else who needs it.
Yeah, well, I sometimes talk with the material engineering department here, and they do a lot of similar stuff that we do in physics, like molecular dynamics, do this kind of bunch of simulations, and also, but since they are since they're in kind of engineering, they also do things through chemistry and stuff. And to me, I never really get chemistry because to me it's such a very macroscopic picture, which is nice to try to understand things, but I'm just like more fundamental stuff. But I can see that material physics or material science has more to offer in terms of like macroscopic scale, designing, engineering.
So in terms of this materials research and kind of chemistry, physics stuff, what did you research?
Yeah, so throughout my research, it was all focused on lithium-ion batteries. But that being said, it's a rabbit hole in itself. I think my initial research was in positive electrode material, and then I went on to electrolyte, and then in my master's it was more negative electrode material, and so that covers the three main aspects of the battery, and currently still working in lithium-ion batteries, but now the electrolyte is a solid rather than a liquid.
Well, just a quick question. I feel like a lot of people, when they hear about electrolyte, they'll think of like
Gatorade.
The drinks. They're just having some electrolyte. Yes, Gatorade. So can you explain in terms like, what to you was our electrolytes?
Yeah. So I mean, Gatorade is an electrolyte. That's a fine electrolyte. Basically, it's a substance that has dissociated anions and cations, kind of thing. It's like salt, basically. Salt in water would be a very good representation of an electrolyte. And in the lithium-ion case, you have a salt in your, like, let's go back to the liquid state diffusion. If you have a salt that can conduct the lithium through the liquid, it can carry the lithium ion through the liquid. And then also you don't want it to conduct electrons. So you want it to be ionically conductive, electrically insulative, and that would be a good candidate for an electrolyte for a lithium-ion battery.
So just taking a step back, just for those who may not be familiar with even the functions of batteries. So what's happening within a cell that makes electricity?
Cool, yeah. So in the cell, you've got, like I mentioned, the positive, negative electrode. Those are relative to whatever chemical potential that they're at versus the metal of interest. And so in the case of a very standard example, the positive electrode may be so like a lithium transition metal oxide, and let's say it's at 4.2, and then your negative electrode could be graphite, let's say it's at 0.1. Then your cell potential would be your positive minus your negative, and so we have like 4.1 if that math was correct, is off the top of my head. But basically, you put lithium in different states, and they're separated where the electrons can't transfer, right? So you would hold them in the, let's say, the charged state. They don't want to be in the graphite because they're more stable in the positive electrode. But when we give the electrons a pathway, like by connecting an external circuit, when the electrons can move, it will always go back to that more stable state, which is the discharge state of having lithium in the positive electrode. And so when you charge it, you're forcing the electrons into the graphite, and so the lithium has to go and meet with the over at the graphite. And so you're forcing them to go where they don't want to go, and then you're letting them go back where they want it to go when you extract that electricity as work.
So, because I try to remember from like the alkali batteries back in the days where it's not rechargeable, because those are basically just chemical reaction, just create electricity, and then the byproduct is just there, and then it's not reversible. So, what's so special about lithium? That's like, is it, you can bring it back? So, like, why? So, is it because the reaction is reversible, or is it some special thing about lithium that only works in its, the periodic table has a group like lithium, sodium. So is this just work for that group, or is there something special about lithium?
Yeah, so the special thing, you kind of touched on it right away, is that it is a reversible reaction. And so it's not strictly for lithium, sodium, potassium, zinc, like you have a decent amount of alternatives, if you will. But it's all about reversibility, and that makes it a secondary energy storage where you can reverse the reaction and therefore recharge your battery. That's what makes them special, so to say. So we're not constantly throwing away batteries. Lithium as well, I forgot to mention, is just so light. So then in terms of your energy density, that's why it's quite a nice candidate.
So I don't know how much of this you can talk about. I mean, trade secrets and whatnot, but so when you worked at Dalhousie, you worked for Tesla, I believe, partially. Like, I don't really know the details, but I remember that being thrown around a little bit. So kind of you were working on these lithium-ion batteries, and I think you said they were liquid they had liquid in them opposed to solid of some kind, because now you're working on the solid case, and we can talk about that soon. But what were you trying to do? Like, how are you trying to make these batteries better?
Yeah, so I was pretty blessed to have early research experience throughout that integrated science program that you were roughly mentioning. And that got me to do a little bit of work in Professor Jeff Dawn's lab, who eventually was funded by Tesla. And I did, like you could say, I guess volunteer work, or like just working in that lab during my undergrad as well. And then I took a small break from undergrad, I think in my third year, to do a internship at Tesla itself. And so the whole time in his lab and Tesla, it's mostly related to degradation. So and like you said, liquid electrolytes. So you kind of work with the the batteries or the chemistries that are applicable to, like they can be used right away, and you're kind of tweaking the electrolyte or maybe a coating or something, and you're seeing how that hurts the performance in terms of like capacity retention or anything like that.
Okay, so you change a couple things, you tweak it, you run it through a ton of cycles, so you charge and discharge your battery, and then you kind of measure some data and compare it to what exists, and
Essentially.
stuff like that, I'm guessing, yeah.
Well, yeah, I think what I remember from Jeff Dawn's talk was that they were looking like capacity retention, but their files was like they always like going slow, and then there's a big cut off where basically the battery would kind of die off, and they turn out to be, I think, the electrolyte, or there's one of them, there's liquid dried out, which I think at the time the reason wasn't really found. Do you have any ideas on that now, or something you haven't worked on that?
I think you were saying capacity retention, and you're mentioning rollover, like where the cell just goes to die eventually, just like
Yes.
Yeah. So rollover can have a bunch of different causes, but what you were mentioning there about the electrolyte, it like essentially it's not a stable system. The lithium-ion battery, it forms an interface to keep it stable. So like if you didn't have this interface, the electrolyte would react with the electrodes just fully, and then we wouldn't have what we have. But it forms this film that keeps it stable, and that film is the solid electrolyte interface, and it keeps it from just doing a runaway reaction. That being said, that can build up over time through cycling, and this structure consists of lithium-containing materials. And so if we use all the lithium that we have, we can't send things back and forth, essentially.
So I'm curious about the cycling itself, because if we look, say, at a phone or an electric car, it takes sometimes years to see the battery degradation. So how are you able to cycle these cells that you're testing in a reasonable time?
Yeah, so I think they have quite a few techniques of sort of accelerating that. I know that they cycle cells for just a really long time, but essentially you'd want to find a way to test the degradation without actually having to have it running for 15 years, and that can be, you can play around with the rates at which you run the cells and parameters such as that. But yeah, essentially mimic it somehow.
How are you enjoying being pelted with our questions? They're pretty simple for you, probably.
Yeah, hopefully. I was planning to talk most about X-rays and imaging and solid state, but I mean, this stuff should be, bread and butter. So if I get anything wrong, it should be on me.
Yeah, we have lots of time to talk about that. So my next question.
Okay.
So this liquid electrolyte, you've now moved on to University College London, where your new group. You said you now work with these kind of solid electrolytes instead. So I imagine there's a reason that I imagine the solid ones, they're better in some aspects and maybe worse in others. So what's the difference?
Elaborate on that.
Why would you like them more? Yeah.
Cool. This will be fine. So yeah, most electrolytes are some kind of form of hydrocarbons with obviously the lithium salt, so that can act as an electrolyte. And by utilizing solid state, we're moving away from diffusion, like in terms of percolation through the liquid electrolyte, into solid state diffusion. And not only is it interesting, but like you said, they do have some proposed advantages. Mainly one that people focus on is safety. So we would replace the flammable liquid that can spill out in the event of a crash with this like rock, this just ceramic thing or whatever it is that ideally will not combust That being said, a lot of the advantages and disadvantages are speculative for now, but there are quite a few. Mainly, yeah. So the safety, energy density as well, can be, you can achieve a higher energy density as they propose. That mainly has to do with the cell construction, where you don't have like individual cell casings, and you could kind of stack the cells together in one big pack. That would drastically reduce the size and weight of the pack. But yeah, very interesting. Sorry, Feely, do you have something?
Yeah, because what confused me a bit was that I understand the concept of liquid electrolytes because you transfer ions and liquids are moving around, but solids the solid electrolytes some kind of crystalline structure? Are they amorphous? How do they transfer ion? Solid is solid, right? If you think about it.
Interesting. I would have thought as physicists that the solid state diffusion would make more sense, but this is cool. Okay. So okay, rather than concentration gradients and all that kind of driving the liquid diffusion, so in solid state you have basically crystallographic defects. That's how the ions move throughout the structure. So mainly you get the Schottky and Frankel defects, which are two different crystallographic defects where the cation and anion can kind of move around. Yikes. Which one is which, though? That is a good question. I think we're not going to go into that because I might get it wrong. One of them, just the cation moves into the interstitial site, and then the other one, the cation and anion move together straight out of the crystal. And mainly in the ones that we're working on is where the cation just kind of moves into the interstitial site instead of its normal site. And so you would have the cation kind of bouncing around, if you will, like more cations would come from the source and kind of bounce along through the solid state, the solid crystal, through these defects, these like point defects, to go to the other side.
So it's gonna be slower than liquid diffusion then, because it's through the crystalline structure, and I'm guessing it's not a tightly packed system because then it would be very difficult. So what type of so it's gonna be made some kind of lithium, right? Because if you think about salt, because I know that salt, like in like table salt, also if you put a big crystalline structure, also conduct electricity and do everything.
Yeah, exactly. So yeah, you definitely need the lithium in there, same as before, and it's like essentially like a lithium containing crystal, and you did hit on like the biggest barrier to I guess you could say commercialization or just utilization of solid state batteries is slow. And mainly, like, we don't think of it as slow, but we think of it as resistivity. So very high resistance compared to liquid. Even like the most advanced superconducting solid state is still only on par with like the liquid. And then they have considerations in terms of their stability. But yeah, there's just a huge amount of resistance, and I guess that's resistance to the market too. But the main argument that they usually hold against that is that, well, it's a solid, so sure, there's more resistance, but we can pump more current through that too without having adverse effects. Because if you want to really pump current through the liquid state, you're going to initiate thermal runaway faster than a solid, is what they're claiming. But I've read papers that also say that the solid is not uncombustible. It's basically just less combustible. So that's another issue. But
so yeah, it's interesting because I'm very used to in crystal structures just kind of saying, all right, everything's. I mean, I don't do solid state physics, but I know a little bit about it, and I'm very much used to like, all right, all these crystals or all these atoms or whatever they're kind of fixed. You assume they're fixed, and then electrons move around, or holes, or you have excitations like phonons and things. So it's interesting that you actually get these ions kind of moving about. So how does this X-ray tomography stuff come in? So I guess one thing is that you mentioned that there's some publications, some people out there who say this might happen, and some people who say the opposite might happen. Are those people who've done tests, or are they like theoretically guessing this? Or are they doing simulations?
I think there's a lot of work in every aspect. Like it's garnering a lot of attention over the last few years, I suppose. But there are like the test that I was talking about, the combustibility, that was done experimentally, and so they're like, yeah, it does combust if you take it high enough, that kind of thing. But yeah, modeling helps in terms of the speed of testing, because I think I read somewhere as of 2021 there are over 18,000 possible crystals that would work as an electrolyte based on the Materials Project, which is this huge database of crystals and such. So we would need the workforce of the computers for sure.
Well, I'm putting my little guess here because you just mentioned X-ray and you talk about the crystal and defects. Are you using like X-ray diffraction to figure out those stuff, or you use X-ray in different kind of thing?
So XRD, powder diffraction, definitely, like, that can be utilized. That's very good. What I was going to talk about more today is X-ray imaging, sort of like medical imaging, if you will, like radiographs and computed tomography. That's more the area that I focus on a daily basis. However, like, powder diffraction comes in all the time, and I do have some applications for that.
Yeah, because sometimes I get confused about X-ray. Sometimes I think about it as like, oh, they're just cathode ray, just electrons, and then sometimes I think, well, is it just like EM wave? Like, that's maybe I'm just wrong, but if you think of the cathode ray, I don't think it's X-ray, but I'm a little confused now.
It's all just light. It's all just light. Yeah, exactly.
Cathode rays are like electrons and whatnot, right?
I think the first X-ray, they shoot electron into something and emit X-ray, right? I think that's where I got this from.
All right. So what are you doing with your new project? What are you using these X-rays for? Because you mentioned to me before you have a YouTube channel, a few videos up, and I saw you were looking at the inside structure of like coins and biscuits and things like that using this technique. So what is this technique, first off, and what were you doing with it?
Okay, that's a lot to unpack. XCT, as it's called, which is why the channel's XCT Chaps. Chaps being a very British thing, I suppose. That's why we kind of went with that. So XCT, X-ray computed tomography, is just utilizing X-rays to gather projections, and then you assemble these projections into a 3D volume rendering with a computer, obviously, unless you want to do that by hand. Basically, like Liam said, it gives you a 3D volume of the object in question, but also the internal structure. So we don't just see the outside or something of those sorts. And so early on with making these solid batteries, right, I thought I was just going to throw them together and then cycle them as normal with all the conventional stuff that I was doing before, and they were going to work perfectly, and then I was going to tweak it and it's going to work more perfectly, and I'd publish a paper. That was not the case at all. Assembling them was just it was very difficult, and so I had to make a lot of bespoke, which is a custom in British slang, so these bespoke cells and things. And what I found out right away is that they were always cracked or forming cracks or just an utter mess on the inside, which you really wouldn't know without this method of imaging. And so, while a lot of researchers around me were throwing them together and hoping for the best, like electrochemically, I could kind of take a step back and say, well, how can I analyze cracks if we start off with cracks or something like that? And so that began my journey into making the most structurally sound solid state battery to begin with. And then I could, cycle it and destroy it and then see what happens. But yeah, it's quite the rabbit hole itself, I guess.
Yeah, but it allows you to see inside of the solid without having to, smash it open. And then you can tweak things and see, is there more cracks this time? Is there less cracks? What's the better thing, I guess. So that's interesting.
Well, I've got to add a little bit for people who are not familiar with the word tomography. It sounds weird. I think it's just the practice of imagining the cross section of a solid using an X-ray or other rays, right? It's to me, it's like, oh, I'm used to the word topology, and like, what is tomography?
so when you do this, the way the program / experiment looked on the YouTube channel was that it's basically like if you took like an object, it looks like a bunch of kind of slices of this object. These 2D slices have all been kind of attached together to create the 3D object. And you can kind of look at each individual slice as you want. So you can say, oh, I want to look like I have a coin. I want to look at what the coin looks like, 0.1 centimeters inside of it. And then you can just kind of look at that 2D cross section.
Yeah.
Well, that's what MRI kind of do, right? MRI imaging to recreate the 3D structure. They take a lot of cross sections and rebuild it. I think there's a mathematical coordinate construction that you have. I don't remember what it's called, but to basically transform it so it works beautifully.
Yeah, I'm sure you guys would love the reconstruction methods because that's just a whole other area of focus. In the videos, I always used a filtered back projection, which I believe uses a Fourier transform somewhere in there. But essentially, that stack that you're talking about is actually the final product that we're getting from this reconstruction. And then what Feely was talking about, where like we're taking all the projections at the different angles while we're like spinning the object. Those files would be what you classify as a projection. You can get like a sinogram from that, and then that's what you construct together. And then the file that you carry around would be a stack of these 2D images, like Liam was talking about. But you can see all the way through the object, the outside of the object. And then when you pair that together with techniques, like image processing techniques, it's a very powerful, I guess, just a method of looking at what we have.
It's always really interesting in science how you notice that everybody's doing something a certain way, and then you're like, why aren't they doing it this way? Like, if they're just making these solids with cracks in them and hoping for the best, it seems really obvious that you would use this method to look inside them, but it's funny because that happens everywhere in science, like all the time. Like, you're like, why are they doing it this way? They should be doing it this better way.
Yeah, I think there's actually a very clear answer to that one. Like, why is no one doing it? Is accessibility. Like these machines are very expensive. The one that I always like show in the the videos is in the hundreds of thousands, right? I think above 3 or 4. But then the moment you go higher resolution, you're getting into the millions, and we're talking about pounds. Back in the day, that was a strong currency. So it's quite expensive. So the accessibility is, I think, a reason why people would not do this so much.
What I'm curious about in terms of X-ray, because when I think about having the variable depth, because when you have like MRI or CT, I kind of make some sense. You can tune certain spins or stuff. But when I think about X-ray, if you talk about normal X-ray, when you go to like a doctor when your arm got broken or something, it basically just find the projection of what doesn't go through. So how you get each basically how you control depth in terms of X-ray? Do you just control the frequency of the X-ray light, or like how do you explore depth using X-ray?
That's a really good question. Yeah, I might have to look more into exactly how depth is controlled, but the way I understand it is that we have a flux of X-rays coming through the sample, and then we refer to it as attenuation, right? Like the interruption of that flux. And so if you have something that's more highly attenuating at whatever distance, and then you have something else, like when it reaches the detector, like that length will be preserved, like that depth of the different levels of attenuation will be preserved when it gets to the detector, is how I understand it.
So I'm curious about the actual construction, because there's cracks being caused when you're making these new types of solid-state batteries. But why? Why are they cracking so much? And what's going on in the construction that's different, say, than lithium polymer batteries or lithium-ion batteries?
Sure. Well, early on, so like we said before, with the conductivity, you would, to reduce the resistance, you'd want basically a solid crystal, no voids, no nothing like that. So with that being said, increasing the density, so like packing it as much as you can, becomes a key parameter in having cells that work well. And so when making these cells, we're actually putting like a ton of pressure on them. I've seen papers that go up to 380 megapascals for the pressure that they're under when they're forming these pellets. And so that's already like pressure that can like break metal or whatever. It's pretty high. I've gone up to like 500, I think, megapascals. And so with these extreme pressures and just what you're dealing with too, which is like a ceramic or something, like you can't break the liquid, so to say, right? But if I put an electrolyte and I put a bunch of pressure on it, maybe it becomes brittle or something like that. Like, so a lot of times with making that pellet, just putting the pressure and then releasing the pressure, you'll find that there's like a crack. And then sometimes it's not cracked, or you don't think it's cracked, and you go to put it in whatever fixture you're working with, and then like there's not a uniform pressure put on it so that it breaks. Like there's many things that can go wrong.
So I have a question, less physics. This is more like a general question. Is you work with X-ray a lot. What is like working with radiation? Because do you have a lot of radiation safety training, or like for like other people? How would someone want to work with radiation? Like, are you getting exposed a lot? Do you have to check yourself every year? Like, what's it like?
Yeah, so there's definitely a lot of training, especially if you want to go to like synchrotrons and such like that. But with the lab-based CT machines, if you ever watch the videos, they have this like giant door. So there's a lot of lead shielding in these lab-based machines. So technically, you should be able to live in that room with no issue at all.
So, in terms of end goals for your research, what kind of things are you striving to do with this XCT and ensuring that there are no cracks in the material?
So what I've been focusing on now is, like Liam said, advanced characterization. So you can throw anything, like a scone, for example, into a CT, and you can do like whatever you want to do. There's so many things you could vary, like the energy of the incoming X-rays, the energy of, or like filtering, like you can put metal filters there. You can collect whatever amount of projections you want. Like you don't really see that in the video, but like there's so many things that you could optimize basically. And I've been making these cells very small, basically, in order to achieve very high resolutions. So at the current date, I'm able to make cells that are below a millimeter in diameter, and I'm able to get resolutions on the nanometer scale. And I'm able to take some of these images in like less than 2 hours. Whereas like conventionally, a cell would be bigger and it would take maybe 20 hours. So like playing with all these parameters to optimize the imaging of these cells was a big win. Additionally, I will be using neutrons for computed tomography as well, where neutrons have a completely different attenuation, like a pattern, I suppose you could say. Like, so hydrogen and lithium, for example, attenuate very well with neutrons, so they would show up very bright, whereas that doesn't happen with X-rays. So I guess for the future of my work would be multimodal imaging, so where you're imaging with different perspectives, be it neutron, X-ray, CT, and then as Feely kind of mentioned, with diffraction, you can also do XRD CT, which is the volume, but then each of the pixels, say, is a different X-ray pattern. And so you can see differences in crystal phase throughout the volume. You can see the high definition spatial resolution of the X-rays, and we could see where the lithium is with the neutrons. And so that would be the big end goal, is to establish and optimize these advanced characterizations in imaging.
What about your personal goal? Was like what did you finish with your PhD? So these are your projects, right? But what's your plan? You have any?
I have no plan. I am just living it day by day. Let's say that.
Me too.
Yeah, but it sounds like what you do have a lot of industry applications. I know, like, I want to kind of go to academia, but do you want to teach?
No, I would probably go into industry. That being said, there's not a lot of industries that let you play with neutrons, I don't think. So it's very interesting. Yeah, we'll see. We'll see when the time comes.
McMaster's got a pretty good neutron scattering community, so if you're ever around, come hit me up. One of our old profs actually used neutron scattering to study food, like milk and cheese and stuff. So kind of relate to what you're doing, but slightly different.
Yeah, it's I just I like gathering different knowledge, I suppose. Like the CT was just so cool, and that's why we started like XCT chaps as well, because a big thing for me, even though I would like to focus in industry, is public engagement. Like it doesn't just help with academia, it helps with everything to do with funding, like the progress of like whatever you're doing. For instance, like everybody's all hyped about space because SpaceX, right? Like like public engagement is at the heart of almost everything we do, and I find that some techniques that I did in the past maybe wouldn't be so flamboyant, if to say. Like if you do powder diffraction, it's like, oh, look at those peaks, right? Like average Joe is not going to care that much, but if you're like, look at the inside of the scone, like that's it's very what would you say, like attainable in terms of like we can all get hyped from it, basically.
Well, we're running out of time, so thank you very much, Scott, for talking to us about all this very interesting stuff. Maybe we'll get you in another time down the road, who knows. But yeah, that was great. So before we wrap things up, Patrick is gonna tell us about ways to contact us, and maybe also mention he's a relevant a topical, I would say, story for us, but I'll let him talk about that.
Okay, so if you would like to contact us at all, whether you're interested in the topics and have some extra questions, or if you would also like to be a guest on our show, much like Scott was today, you can email us. We are hyperthesispodcast@gmail.com. You can also find us on Instagram. We are at the Hyperthesis. There you can follow us. We send weekly updates whenever we're posting a show, as well as some fun updates in between. We'll be trying to use that a lot more for updates this season. And we'll also be referring to other people's contact information should they be a guest on our show. So if you have any questions, feel free to either contact us over email or over Instagram, and we can be found wherever you find your podcasts, whether it's on Apple Podcasts, Google Podcasts, Amazon Podcasts, Spotify. We're based out of anchor.fm/the Hyperthesis, and you can find us anywhere. And if you'd like to contact Scott in any way or check out his YouTube channel, Scott, how can people contact you if they are interested in learning more about XCT or want to see your YouTube channel?
I guess they could subscribe to XCT Chaps, and maybe I'll be engaging in the comments section. I don't know.
Well, at the very least, check out XCT Chaps on YouTube for some very cool things, including looking at what's in your candy. Some very interesting stuff there. So moving on to the final story for today, it's just going to be a quick one, and it's pretty relevant, and it's just a little bit of a history on batteries. So Scott, if you hear some misinformation or something that I got wrong, feel free to interrupt and set the record straight. But we're going to look back at batteries as they were well over 2,000 years ago, starting with the Baghdad batteries. Now, batteries have been around a lot longer than most people expect. So we have batteries everywhere nowadays, from our phones to our cars to really most things have some sort of battery in them, whether it's a rechargeable battery like the lithium-ion batteries, or if it's just a single use, it's done and you throw it away kind of battery. But little do people know is that batteries have existed since the BC days, or the BCE days, depending on how you say it. And these first batteries, the Baghdad batteries, are thought to have been invented by the Mesopotamians, who are one of the first societies and civilizations that evolved within kind of the Middle East area. And they're called the Baghdad batteries because they were found in and around Baghdad. Now, these batteries were made of ceramic pots with an electrolytic solution inside. So very similar to batteries that we see today, there's electrolytes, and they had an iron bar and a copper cylinder that surrounded that iron bar. And these two were submerged into this clay pot filled with electrolyte, and they actually produced a voltage. Now, we have strong evidence that these were something that were used in a fair amount. So there's quite a few that were preserved over 2,000 years. And again, it's very similar to what we see in batteries today, or at least within the past couple centuries. Now, these Baghdad batteries, as they're called, were thought to be used for electroplating of materials. So that's using an applied voltage to stick one metal essentially onto another. But we're still not entirely sure if that's what they were used for, if they were used for some healing properties or pain relief. However, if you check out, I believe, one of the earlier Mythbusters episodes, they actually built these and tested them and got some decent shocks from them too. So these were actually effective batteries. Now, the mechanism behind these batteries wouldn't be understood for another 2,000 years, pretty much, until 1780, when Luigi Galvani, an Italian chemist and / biologist, discovered the electrochemical process that led to a current being produced when two different metals are in the same electrolytic solution. So much like these Baghdad batteries, he took two dissimilar metals. So in this case, he took a copper wire or a brass wire and an iron bar, and actually placed the iron bar next to a frog so it was touching, and then wrapped this copper wire around a frog leg, and the frog leg started twitching. Now, this might seem kind of silly and weird, but as a biologist, it makes sense that you would want to be testing this. And so, if you have this iron bar and this copper wire, the frog itself is acting as the electrolyte. And so, Galvani was the first to really note down this process, and that's why it's now known as the galvanic process, which we use for a lot of different things today. Now, the term battery itself wasn't used. Well, it was used a bit earlier by Benjamin Franklin in 1749 when he was experimenting with electricity, but he didn't really go much into what we consider batteries today. Now, modern batteries today were invented a little bit later on by Alessandro Volta. Now, I believe we mentioned this before in some previous podcast episode, but Volta was actually inspired by electric eels and how their cells are stacked to produce electricity and an electric current within the bodies of the electric eel, but their cells are little, almost disc shaped that are stacked, and across each cell is a voltage. And so if you stack a whole bunch of those cells together, you're able to produce a larger voltage, which is exactly what these electric eels did. Now, Volta said, well, what happens if we take two dissimilar metals, so in this case, let's say copper and zinc, stack them, and then add another layer of copper and zinc, and another layer. And this became known as the Volta battery, where he was able to stack all of these different cells on top of each other and produced significant voltage. Now, this was done in 1800, and just for zinc and copper, they had a voltage of about 0.76 volts. And he also worked with different metals, which produced different voltages. As Scott mentioned earlier, there's different potentials that can be produced with different metals. And so Volta also played with this. Now, copper and zinc were effective cathode and anode materials at the time, but there were other materials that had yet to be discovered. And with Volta's initial battery, advances were made throughout the 1800s, with another popular invention being the lead-acid battery. Now, invented by Gaston Planté, I believe that's how it's pronounced, this was the first type of rechargeable battery. Now, before then, as we again discussed earlier today, we have batteries that are rechargeable, batteries that aren't. Now, the lead-acid battery, which you might be familiar with, especially if you've worked on cars at all, or even drive a car, uses a lead sulfate and sulfuric acid to both discharge and charge. So there's the sulfuric acid as the electrolyte, and then you have this lead sulfate plates. And this was phenomenal at the time. And even today, it still blows my mind that it's so old, given that it's from 1859. And this durable battery could have a voltage applied to it, and then it would recharge, and then you could use it again and again and again. So as anyone that's owned an older car knows, you do have to replace them eventually, but they do their job. And a fun fact is that even electric cars still have this 12-volt lead-acid battery because they're needed to run a lot of the electronics within the vehicle. Now, there were a lot of big advancements in batteries throughout the years, some of which we've talked about with Scott. But the final one I want to talk about is the lithium-ion battery itself, and just a bit of a history of that. Now, work was done on it since the 1950s, 60s, but there wasn't really any viable solutions, partly because lithium is not necessarily the safest material, especially when it is introduced to air. But in 1980, an American physicist named John Goodenough, and yes, that is his actual name, John Goodenough, along with several other physicists and chemists, invented a battery that used lithium ions to be able to migrate from one electrode to the other. Now, while, again, work had been done before, this was a stable battery, but it wasn't prevalent. It didn't become prevalent in the 1980s because of some issues with it, including dendritic formations at the electrodes, which led to it short-circuiting, and again, big explosions and issues, which I'm sure if you Google Tesla's being on fire, you'll find plenty of examples of that. But after years and years of development, there was enough interest by Sony in particular that they wanted this type of rechargeable battery. So they were the first company to actually mass produce it. Now, there was work by Akira Yoshino in ensuring that these batteries were actually stable and usable, and Sony developed these ideas and were able to mass produce them. And 3 people, so good enough, M. Stanley Whittingham and Yoshino, all won the Nobel Prize in Chemistry for the development of lithium-ion batteries. And that was pretty recent too. So, given all that we've discussed today about lithium-ion batteries and the upcoming solid-state batteries, and who knows what else is in the works right now, but considering the prevalence of these batteries, and they're becoming everywhere. They're in phones, they're in cars, they're in mass storage units for grids. They're definitely fundamentally changing the world as we know it, hopefully leading to a greener future. But based on the work that Scott's doing and that other people are doing, maybe we'll be able to replace them someday with something even better.
A wonderful story. It was good enough for me. Anyway, awesome. Thank you so much, Scott. That was great. And yeah, that's everything. So we'll see you next time, everybody.
All right, take care. Thank you, Scott.
Thank you, Scott. Bye, everyone.
Have a good one.